All right, go ahead.
Hello, future programmers. You're watching the 2020 code review. All right, so we're going over the project directory structure. So there's a lot of automatically created stuff in our main directory, like all of this .dylib stuff is like macOS. You don't need to know all this. There's the class files. You don't need to know that. The main stuff that you'll be mostly working with, well, programmers mostly work with is this source directory, and that's where all of our code is located. So inside the source directory, there's the main directory. Inside the main, there's the Java. Our package name that we code under is called java.frc.robot, hence the structure of Java frc robot as the subdirectories. Inside here is where all of our Java code goes. And from there, we also have a separate category called commands. And we also have another thing called subsystems. So, Summer, scroll up. So we do have a main.java class, and that's where we don't do much, but that's essentially where all of our code starts. In the oi.java class, I think we have, all right, let's actually start going through these files. I think that would be most helpful.
All right, should we start with main?
Yep, let's start with main. Yes, I remember this from last year. So we don't do much here. All we do is that we just, essentially we just call a single method on a class called robot base. So we initialize a new robot object and we just pass that in as a parameter to robot base. And we're like, so here's the robot object. Now go start this.
All right, OI next, or do you want to do?
Let's go to robot.java.
Yeah, okay.
So this is the class of which we created an object of, and we passed to start robot. So this is what was the argument. So we first import all of our like library stuff at the top. Yeah, we'll go over this in more detail probably later. But essentially what we're doing here is that we're creating a new class called robot. Our super class is timed robot. Timed robot is a class that comes with the WPI lib framework that we use. We make some just some constants here. So we're like declaring these subsystems. That's an important part. By this, we're just creating we create objects of every subsystem class that we make, and we'll go over how the subsystems factor in here. It's difficult to explain each part because this is a huge complex program. So we're just gonna jump right into it and hopefully we'll cover everything. So when we start the robot, we call the robot init method. What it's doing here is that it's just communicating with Smart Dashboard. So last programming meeting, we went over the Smart Dashboard and how it's able to take in data and also spits out stuff. So it's just selecting which autonomous we selected for it to run. It's getting that, and it's initializing all of the subsystems. So here in robot periodic, so this is actually kind of important. So how the robot actually works is that it runs a loop every 40 milliseconds or something. What it does is that it gets inputs from the joystick and sensors. It performs calculations and runs logic on those inputs. Then it assigns a value to whatever motors and transmits data back. And that happens every 40 seconds, which is why we call it robot periodic. Now,
and then there's like a scheduler that does all of this for us.
Yeah, and that's why you can say, that's why you see like scheduler.getInstance.run. So in every subsystem, we also have a periodic method, and that subsystem oversees what we do every 40 milliseconds. So the scheduler object is just saying, we're gonna leave all of this robot periodic stuff to the scheduler, and we also have to connect each of our subsystems to the scheduler object as well. I hope that makes sense. We'll go over that in a bit. So here we talk about autonomous, and this is the initiation code for autonomous. The first line of code is we are selecting which autonomous to use from our Smart Dashboard. And then we run switch statement. If we select one thing, do this. If we selected a different autonomous, do this. The shooting autonomous is like, last year there was an opportunity to score points by shooting our power cells into the power port. So the shooting autonomous assumes that we have 3 power cells that are loaded and we're like primed to shoot. And it performs an action where we use the limelight to automatically align ourselves with the target and launch the balls. With the initiation auto, that's assuming that we have 2 other robots on our alliance that can shoot the balls better than us. So we don't need to do that. All we need to do is just pass the initiation line, and that gives us 5 points.
Yeah.
So that's essentially, yeah, go ahead, Sandra.
Yeah. So yeah, the other thing with like, so the reason we have like 2 autonomous is because we were actually like developing our shooting auto at competition, since that was just kind of like an ongoing process, since we didn't really have like access to a field very easily. And so we started competition with an initiation auto, but then like as we like tested at competition, we were able to get ourselves a shooting auto that actually worked pretty well.
Yeah, and that's why we have those options essentially.
Yeah.
So this is the autonomous initiation code. It runs like for the first time when we start the autonomous. Now we have the autonomous periodic code, and this runs every 40 milliseconds. Wait, actually, yeah, 40 milliseconds. So what it does is that if we selected a certain type of autonomous, it would, hold on, that code's actually not right.
Yeah.
Do
yeah,
not.
I mean, like, yeah. So we initially had something there, but it was supposed to be in like the initiation.
Yeah, that was
like the
supposed to be
auton
initiation.
in it instead of the auton periodic. So
here, let me explain why. Because what it's doing is that in case one autonomous is selected, it's supposed to start a command. And it's saying like, instead of running the command every 40 milliseconds, it says to start one. And that should actually be in the initiation, because we just want to start a command and let it to run. So we'll go over commands and subsystems in a bit, but that code is not supposed to be there.
yeah, it's all commented out. Yeah.
Yes. Next thing, same thing with the periodic code, like the teleop periodic. So essentially,
Yeah,
it literally says very important, do not remove, and then it's
I'm pretty sure we had our
commented
teleop
out.
periodic. Well, actually, that's robot periodic. Huh? Weird.
Huh, that's pretty funny.
Interesting.
Wait, let me take a screenshot of that. This is, okay, all right. All right, so now let's go to oi.java. Our code is a mess, oh my God. Okay, so oi.java is essentially just, it manages a bunch of our inputs. And the way that the WPI library like framework does is that we don't have to code all of the USB like the communications over USB to the joystick itself. So the WPI lib library like already handles that. All we need to do is just create an object that represents a joystick button. We pass in a controller object, and we pass in like which button it should target. So here, what we're doing is that we're creating a controller object. Robot map.joystick, which is the parameter, just refers to what USB port it's on. WPI lib is going to handle like talking to that joystick by itself. Then we create a bunch of the buttons that we want it to track. And we do this by creating joystick button objects. We pass in the controller object, which controller it's on. If we had 2 controllers, we would need two joystick objects, controller and controller like 2. We also passed in like which button, and those are like constants, and they're given to us by WPI lib.
Well, I mean, okay, so those constants, I think we can actually get those using Phoenix Tuner.
Sorry, I'm wrong. Actually, yeah, we did have to manually find those.
Yeah. Okay. Yeah. Sorry. No, they were in the driver station. The motor constants are in Phoenix Tuner.
Yes.
Yeah, and then yeah, here you assign commands to when you press them and stuff.
Yeah. So essentially, we're saying when one button is pressed, we want to start one command.
Right. And then this might be a little confusing because like we have our Logitech controller here, but we also had another controller, and that was actually a button board. And so we would actually have 2 drivers at competitions. One would just be like actually driving the robot, and then the other one would be like handling like all the functionality in the robot. So like if we want to shoot a ball, then like they would handle it using the button board. And so if you see here, yeah, we have like another joystick that's a button board, and we would assign it its respective functions. Right.
All right, let's go over robotmap.java. Alrighty. So this is where we store all of the constants of where everything is located. So the main thing right here, yeah, it's all commented. So you can essentially see like buttons on controller, like each of those like numbers refer to a specific button on the controller. And these are all parameters that we have to pass in when we're creating our button objects with WPILib. So WPILib basically knows where to talk to.
Yeah. And then also like here we have our motor mappings as well.
Yeah,
And
and we get
yeah,
those through Phoenix Tuner.
yes, exactly. All right. I mean, okay, I guess PID is kind of like a throwaway. I don't know why we still have it.
Yeah, okay. All right, so let's go into subsystems. The first one that I want to talk about is drive base. So some of y'all might remember that in, I believe it was robot.java, what we do in robot init is that we create a new drive base object. So this is where we define that drive base class that we create an object of. So here we extend the class called subsystem. We define our constructor. And what our constructor does is that it gets those values from robot map that we just went over, where all of our motors are located, and it creates motor objects for those. So it's like Talon SRX and Victor SPX. Those are references to the type of motor and motor controllers that we're using. So it creates those, then it initializes them by saying like factory default mode, and then it sets a neutral mode for those. So it sets like the brake mechanism for those motors. So that's advanced stuff. We might go over that later. You can find more about that in the documentation, but essentially what we're doing here is that we're initializing the motors and we're defining how they should operate. The final two lines of that method, we just say that the left, here, so we say that one motor should follow like the main right motor, and we say that the left motor too should follow the left main motor. And what this allows us to do is that we can treat two motors like as one motor. So two of the motors on the right side of the robot can be controlled by like just in the code referencing one motor specifically. And one of those motors will follow the main motor.
Exactly. And then the drive method. What the drive method, basically what we have here is we have like, so how we drive is we control the speed of our left motor and our right motor. And based on that, it'll like, I guess like move. And so here we're like just setting the, I guess like the percent output based on the controller. So based on like how much we move the joystick, it'll set the right motor.
Here, okay, so there's actually an very important distinction. So this drive method, it's gonna take any numbers that we give it, the left speed and the right speed, and it will not process them at all. It's just gonna assign them like straight to the motors. The processing of that, like what Samrat said, like taking it from the joystick is gonna happen later. And this is really important that the processing doesn't happen here, because we're gonna talk through how that happens. And that's really important on the next method, Samra. It's very important. It's init default command. So the way that subsystems and commands work. So subsystems refer to a specific hardware implementation or a structure. So for example, the drive base is a subsystem. The elevator would be a subsystem. And commands define the functionality of how they work. So here what we're saying is that like, so subsystems might be like certain types of hardware, but commands would specifically give that hardware instructions on what to do at any point in time. So there always needs to be something telling that subsystem what to do. The initial default command method here is saying that if there's no command that's running on that subsystem, create an arcade drive command. And that arcade drive command is going to be that thing that's running every 40 milliseconds, getting what's being inputted on joystick, calculating what the left motor and the right motor should be. And then what it does is it calls the drive method here.
Right.
If that makes sense.
Do we want to go to the arcade drive command or?
Yeah, here, let's go to the arcade drive.
Sounds good. All right. Am I blind or is it not here?
Bro, where did it go? Go to default commands.
Oh, yeah. There we go.
Okay, so here. So most of this isn't important. The constructor is important. So what we're doing is that we're calling a requires method, and that's saying that this command depends on that drive base. So whenever, like when we call the requires command, it allocates that subsystem to this command, and it can't be used by any other command unless this one is interrupted. And I do think that the requires method will interrupt other running commands. Like if we create a new arcade drive object, it will interrupt other commands that are using the drive base, and arcade drive will take superiority. So yeah, that's that. We do need to call that requires command to specify like which subsystem is used. Oh no, Joanne left. I wonder what happened.
Oh no, it's fine. All right.
All right. So yeah, next
Okay,
is
wait. I have a question actually.
Yeah.
yes.
So with that requires command, are there like different tiers? Because like if you have two different like things that call requires, then which one takes priority, basically?
Whichever one is calling it like
Whichever one calls it first, basically.
No, whichever one calls it later.
Oh, okay.
Yeah, I mean,
just make sure that nothing calls it, essentially.
Yeah. All right. Execute. Do you want to go over this, or should I?
Yeah, I can go over it.
All right.
So the execute thing, as you can think of, is probably the thing that, so scheduler automatically runs the execute command every 40 milliseconds. So first two lines, what we're doing is that we're getting the raw axis inputs from the left axis and the Y, like the right, like the left and right axes on our joystick. We're assigning those to our variables. Then what we're doing is we're doing some fancy math where we essentially convert them into like scaled speed and scaled rotation. We want to have some sort of scale, like we don't use a linear scale here. We want, yeah, we use like a Cortex like thingy. Essentially, when we move the joystick a tiny bit, we want our robot to move very small. When we move our joystick a lot, we want our robot to move a lot. So linear scale isn't good enough because it doesn't give us that fine control when we move it a tiny bit.
Yeah, exactly. And then here we're just calculating our left output and right output, which we're going to assign to our robot that drive face that drive. If you remember the other method in the drive face class. The reason we have it negative is I think we put in like one of the motors the wrong way or something. And so
we know, Samrat, the motor is literally in reverse because think about it.
Okay, you know what? Yeah, exactly. But yeah, so just based on like the direction of the motor, it might be negative, it might be positive.
Yeah, because one motor is pointing to the right, right? If that's positive and you have another motor that's on the left side, then obviously it has to be negative.
Yeah.
But, yeah.
And then the other thing you want to note is we have like a left out times equals drive mode. And so like usually like your robot is very fast and it's very hard to control if you just leave like the output speed at like the regular value, and like it's almost like uncontrollable. So what we did this past season is we had two modes. We had a very fast mode and we had a slower mode. And so if the driver pressed a button, they could change modes basically. And this is what this would do. There is one thing you will want to note. You don't want to put this in here. Okay, so yeah, you don't want to put like you don't want to put this in like here because for one reason or another, it just doesn't work. I think we like made this mistake in our rookie season. But then, yeah, so we just took it out and then it works fine now. But yeah, so like make sure you do all your calculations and then you just put the final value in your method.
Samrat, that's not how Java works.
Okay, my guy.
Okay. All right. All right. This worked.
It compiled, fine. So.
Yeah. Wait, can we go over what the drive mode value was like this season?
Oh, yeah.
What was it like?
Yeah, so the fast the fast value was 0.8 because like if we kept it at 1, it would just be like pointless to use since it's just so fast you can't really control it.
Okay, so here everything is coming together. So in oi.java, remember how we set up all of those controllers? Well, on one of the buttons, we said like when pressed, run this method, and that method was change drive mode. So Yeah, everything's starting to connect together. So that calls this method, which then changes the drive mode. And then when the next time the execute is called, right, it uses the new drive mode value. And then that calls the subsystem, which applies the final value on the motors.
Cool. Yeah, we can just go back to another one of our subsystems. I think index is pretty similar to like drive based. Do you want to like color sensor or limelight? Oh, let's do limelight. I think limelight would be good.
Okay. Yeah, so Limelight, remember these subsystems are mostly like packages of hardware. So and they just provide methods for our commands to access that hardware. So for example, in our drive base, we had those motors, and the drive command allowed us to set values to those motors. Now in the Limelight subsystem, essentially what we're doing here is that we're creating like this class that represents what our Limelight is, and we're providing some sort of interfacing between the Limelight and our code that we use in our commands. So some of those commands might be like align with the Limelight, but in order for it to align, it needs to be able to get those values from the Limelight itself. So Summer, can you scroll a little bit?
Yeah, wait, Anant, I think it'd be good to explain what a limelight is actually.
Oh, yes. Okay. So a Limelight is like, so it's like a module that an FRC, so this is actually pretty interesting. So there was an FRC team prototyped a vision system that they ran on like a Raspberry Pi using a webcam. And what they did was that they made it into like a small module, and it worked really great for their season. And there was like interest from other teams. So they started selling this as like a commercial product called a Limelight. It's basically a small Raspberry Pi with a really good camera with a lot of LEDs on it. Like I'm telling you, those LEDs are bright. I
have PTSD from them.
Yeah, it's really bright. It's like a small vision system, like module thing that you can mount on your robot.
It's basically a computer vision camera.
Yeah, essentially. So, and that connects to the robot over Ethernet. So we need to provide interfacing methods for that through this class. So you can see that in our public method, what we're doing is that we're using the network table API. It's like, the network table API is the thing that's provided by WPILib that essentially oversees communication between robot radio, the RoboRio, and the Limelight. So essentially what we're doing here is that we're creating these entries in which we can communicate with the Limelight.
Okay, go back up for a second.
Yeah.
What's with the 90.75 minus the 40.25?
Oh, yeah. So there's comments. So yeah, that represents the height of the target in inches. We had to do a little bit of trigonometry. So remember that the Limelight, we use it for vision processing, and we were using it to detect the targets. So on the power port, which is essentially the target that we shoot the balls at, there were reflective pieces of tape. And the Limelights have really good like LEDs, right? So it bounces off and it illuminates them. So with the Limelight, we're able to track those, and we were using it so that the robot could automatically align. So all we need to do is go near that thing. Then like the driver number 2 on the button board just presses a button, the robot automatically aligns, and you press another button and then it shoots the balls.
Yeah, and then just to explain this, I believe this is like how high the target was in inches, and
you
this
just
is how
kept them
high
separate
our
to like change
robot
them
was.
in case you need to change them.
Yeah, basically. But yeah, that's
because I was wondering why you would have 2 different values, not just like literally put like 50.5 rather than that minus
that.
It's
just like easier to like, I guess like
that was bothering me for a
change them.
second there.
Yeah. We just don't want to do math.
Yeah, that's true. That why would you do math when you have a computer in front of you? All right.
Yeah.
So the constructor. So, okay. So basically, there's like a couple of like, I guess like value table values. And so TX, I believe that is the skew angle like in the horizontal direction. TY is the skew angle in the vertical direction. TA, that's something about area. I don't quite remember. Do you remember, Anand?
Yeah, what percentage of the total area is the target acquiring. So it has a bounding rectangle on the target that it detects. So
Okay, gotcha. And then TS, would you happen to know what that is either?
yeah, I don't think we use that.
Yeah, I don't think we use it either. And then so for the LED modes, basically you can like turn on the LED or turn it off, or you can like have half of it on, half it off, and so we could control it using the LED modes. The pipeline, I so I think you can like there's like different like modes you can set with like the Limelight, and so like if you like you can create your own mode, right? And then you save that to a pipeline, and then the Limelight will automatically use the pipeline you specify. Um, Camera mode is that well, like, there's different modes for like the camera as well. I don't quite remember what they are, but
Yeah, resolution and frame rate.
right, okay. And then we have just a connection method, just check if our limelight's still connected. All right. Um, okay, so we have a get instance method. I think it's pretty self-explanatory. Get table, those are just getters. Okay, yeah. So, oh yeah, so we had a way to like calculate the distance our robot was basically from the target, and we used just a bit of like a trick for this, but it's just like mostly math, and then just putting into code essentially. Let's see. Yeah, so yeah, we use like we use the limelight angle, and then okay. I mean, I don't really remember the math too very well, but I guess
Yeah,
it works
okay.
out. I guess that's how it works out, I guess.
All right. So actually, Cooper, with the thing that you were talking about, like that statement, the minus thing.
Yeah.
So that is the height of the target minus the height of the robot, or like
Yeah.
the height of where the limelight was on the robot.
That's what I was thinking it was.
Yeah. So
It's just weird.
yeah. So that returns that essentially calculates
Imagine
the
not
distance.
using variables.
Oh, bruh. Honestly, yeah, but that method just returns the distance to the target, as you can probably guess. All right. So read variables.
Values.
This essentially just gets all the variables from the Limelight through the network cables, and then it just puts them on Smart Dashboard. There's literally nothing else.
Yeah. Mm-hmm. Oh, we had a debug method.
Yeah.
Or not method, but piece of code. Check connection. I feel like this is copied code from somewhere because I don't remember what this does.
Yeah, I'm pretty sure this is copied. All right,
Yeah.
let's keep going.
That's fine.
Set LED on, set LED off.
That's expected.
Yeah.
And then yeah, you can have the LED blink, I guess. Oh, okay. So there's a vision mode, and then there's just a regular driver mode. That's pretty cool.
I don't think we ever use these.
I don't think we did either. Yeah, so we can get the horizontal offset, vertical offset, get target area, oh, it's a skew amount. Okay. Yeah, and then I guess that was it, right? Yeah. I mean, like so the bulk of this is mostly just with like getting the values and then like having all your like network table entries.
Again, the idea of subsystems is to provide an interface with your hardware. The commands are where the real processing happens. The subsystems are just there to provide communication. And that's why we have all of these like getter methods. And the subsystems are like in the commands are where we're actually going to be like, okay, get the area. So what is the distance to the target? Move forward until this distance, then start this command to shoot the ball. All of that logic happens in the commands. This is just to interface with the hardware.
I had a question. Sorry if this is a bit off topic, but on the WPI Lib docs, it says that they've done a rewrite this year. So is this using the new version or is this the old version?
Is it a 2021 rewrite?
This is 2020 rewrite
okay.
of the command system.
Yeah, so this is using 2019's version because we were too lazy to switch last year. Not gonna lie. But yeah, we'll probably like switch like this year if there is any coding to do. If not, and y'all should definitely switch next year because you do not want to be using 2019 and 2022.
Is it basically the same thing as this, or is it?
It's very similar. There's some like new features, but like a lot of it's like very similar. It shouldn't like drastically change like what you're like eventually going to learn with the new.
So it's okay. So in terms of the structure, it's mainly the same.
Yeah. The structure is like basically the same, I believe.
Okay. Thanks.
All right. Let's see. Let's go to commands. Oh.
What was the default command for Limelight?
Oh, great question. I don't remember. Oh, update limelight. Okay, interesting.
Oh yeah, that update limelight command. Okay, yeah, actually go to there. All right, so let's see.
Okay, yeah,
Oh
it's
yeah,
just
in
like
that
getters and setters.
yeah,
Or
in
like
the
getting them.
execute, that's the main part. What it does is that it sets the values and then it reads the values.
Right. Okay. I think like the alignment stuff is the bigger part, I guess.
Sure.
Yeah, the rotation alignment.
Okay, this part is a little weird because this actually relies on two subsystems. How interesting. Um, oh, this is that weird thing. This isn't a separate command by itself. It's actually one command in a group of commands. So the beauty of commands is that they're modular, right? You can start a command and then you can have it finish. So remember when we were talking about that button board and we said like when you press this, it automatically aligns? Well, there's a lot of forms of alignment. There's rotational alignment, there's distance from the target alignment, there is, all sorts of alignment. So you can have separate commands for those, and you can have one command called align that just calls these three commands and waits for them to finish in sequential order. So this is one of those things in that sequence. So rotational alignment. So we're just going to go over this. This does not require the limelight. This instead requires the drive base, because it's actually going to be assigning values to the drive base, not the limelight. But it does use the limelight. So in execute, every 40 milliseconds, this is what it does. It gets the TX. So yeah, it gets the horizontal value of the detected target. If the value is over 3, I think that was radians. It wouldn't be 3 degrees.
I mean, okay. Yeah, so yeah, degrees, radians. Right, yeah. Well, okay.
Oh well.
Isn't 3 radians a lot? Yeah, that's a lot of radians. I think it's degrees.
Oh yeah. So
Yeah,
okay. So
yeah,
it's
it's
saying,
degrees.
yeah, if it's saying that the target isn't aligned within 3 degrees, drive towards that. Drive towards that at that
yeah, well, you
speed.
would rotate towards it.
Yeah.
Yeah.
And you would rotate at a speed proportional to the distance you were away from that target in terms of rotation.
Well, okay, here. I think a better way to explain this is like, okay, so the reason we have that line is like if math.abs is greater than 3, the reason we have that is if we didn't have that, our robot would continue to rotate like indefinitely, and so we need that threshold because our robot cannot be like exact, since that's not how our world works. And so with that threshold, we're actually able to like exit this command, and so the robot can do other tasks. And then after that, so we're basically just rotating our robot um, at a speed proportional to the rotation angle. So like if we're rotated very far, like if our robot's like if a robot like is not aimed at the target at all, then it'll rotate very fast, and then as it gets closer to the target, it'll slow down so it can be more precise in its actual like I guess like rotation. And then after that, so like once it's in 3 degrees, it'll say it'll like finish the rotation. So it'll set the rotation finish variable to true. And so this like is finished method right here. Well, it returns the rotation finished. So like once we're done like rotating, it'll just it'll exit the command basically.
Okay, so actually it's important. So it's important to talk about how the command exits. So the scheduler command is also like calling is finished repeatedly to check if that command is finished. If it is, it's going to yield control to that subsystem to any other command that wants to take control of it. If there's no command queued or something, honestly, I don't even think there's a queue, but like if no command takes its place, then it's going to go back to that subsystem and it's going to call start default command. I hope that makes sense, right? Like it's going to start a default command that uses that subsystem. So that's what the is finished method is for.
Yeah, cool. Do you want to go over like one of the autonomous commands or?
Actually, we're running pretty late. So do you want to go over anything?
Yeah, I think we can go over one more command, I think. Or like one more file, I guess. Or
Okay.
wait, or here, how about we go over the what's it called? The command group.
Oh, yes. Okay.
Is it manual line? Yeah, command group. Yeah.
All
Yeah.
right.
Okay.
So
Actually, okay. So the other thing you want to like notice before we do that, we have another alignment command. So for our first alignment command we looked at was the rotation alignment. This one is very similar, but it's for distance. And so basically, how our robot worked was it would first like rotate to make sure it's in the correct angle of the actual target, and then after it's done rotating, it would drive forward to make sure it's in within just like shooting range. And so this is what that does basically. There's some more like math to it, I guess. It's not too complicated actually, but that's that. And so after we implemented that, we had a command group, and that's what we call manual line. Anand, do you want to talk about this?
yeah, sure. Okay. Um, yes. So as Samrat said, we have a bunch of different commands, and all of them are related in that task that they're used to like align the robot. So when we press that button on the button board, we start this thing called the command group, and this command just queues all of the sequential like commands. Okay, so the first command that it queues is the rotation alignment. So it's gonna execute the rotation alignment like function. It's gonna call it every 40 milliseconds. It's gonna be checking the is finished method to see whether it returns finished, like true or false. If it returns true, then then obviously like that command ends. And then the next sequential command that's queued is the distance alignment. And that's going to run every 40 milliseconds until that returns is finished. Then it's going to call the rotation alignment every 40 milliseconds until that's finished. So we're just like sequentially queuing these commands to execute.
Yeah,
So,
and then oh yeah. Yeah,
so
so oh
okay.
okay. So just like one like confusing thing here might be like, oh, why are you calling rotation alignment twice? So like sometimes when you're like going forward, like your robot like kind of like is just like it's not directly in front of the goal, and so you have to rotate again to make sure like your shooter is actually like directly in front of the goal. So we call it once, and then we like go in the direction, and then we call it again just to ensure that our robot is like in shooting position and can actually make the goals. Are there any questions over that?
Yes.
All right. Cool. Do y'all want to go over one more command, or we can go for one of the autonomous commands if y'all want? Yeah.
Sure, why not?
All right. So, actually, aren't the autonomous commands very similar the to the regular commands, except for the
Let's do
fact that
initiation. Let's do initiation auto.
yeah.
So remember how we said that, there was one autonomous mode where we just went, like we didn't have the balls preloaded and we just wanted to cross the initiation line. So that's this command. So it's going to call the initiation auto command. This is a command group. Wait, what the heck? Okay, yeah, this is a command group with literally just one command in it. It calls the drive backward command. So the parameters that we're passing here are, so we're saying run the drive backward command at 0.4 speed for 3 seconds. That optional parameter is a timeout in seconds. So if the command hasn't finished by then, just cut it off. So
Yeah, and the reason we have it in like a command group is so we can like use that timeout, because like obviously like if we didn't have it in a command group, then we just say like drive backward, right? Just like the regular way using the robot to drive base. But like the reason we have this is so we can use that timeout. And then yeah, so like autonomous commands are basically just the same as like regular commands, except for the fact that in the robot.java file, you're actually calling them in the autonomous methods rather than the tally-up methods. And yeah, so that's that. We had an index.shoot. All right. Are there any questions about any of these, or like just anything? All right. Here. In that case, I will stop the recording.